Welcome to the next chapter on the proof of Fermat/Theorem, everybody. We're going to be looking at the flat deformation functor in effort to try to close in a few of the gaps remaining in the proof of R equals T. Let's get to it. Today will just be a quick little introduction. We'll let E over Q be a semi-stable elliptic curve, and we'll let P be a prime. Recall that in the proof that E is modular, we saw heavily that properties of the local representation, rho EP restricted to GP. So this is kind of the action on the p-adic Tate module of E restricted to the place P. Properties of this guy played a huge role, okay? As we will see, and as we have already seen, if E has either ordinary or multiplicative reduction at that prime P, these properties of rho EP GP can be described representation theoretically. The problem is when E has supersingular reduction at P, this is not the case because rho bar EP restricted to GP is absolutely irreducible, unlike in the other two cases. Now, instead of looking representation theoretically, though, you can appeal to algebraic geometry. For all n bigger than or equal to 1, we know that the finite discrete GP module, rho EP restricted to GP, mod p to the n, has the property that the associated QP group scheme arises as the generic fiber of a finite flat ZP group scheme, which is commutative of order p to the 2n. So again, like at p, the p-adic representation has algebraic geometry that we're interested in. This has been a theme for the whole, series of talks so far. So what do we do about this? Well, the flat deformation problem is now the tool of choice to deal with this case. Its representability having been shown by Ramakrishna in his thesis when P isn't 2. The main tool used is Fontaine's equivalence of categories between the category of finite flat ZP group schemes of P power order, which we have here, and a certain category of finite length ZP modules with some extra structure that we'll get into later in the chapter. This was originally detailed in Fontaine and Fontaine-Lafay. I think I'm saying that right. I'm not sure. Okay, so these papers have been referenced before. I'm not going to, relist them out or anything like that. So what are we going to be doing here in this chapter? First, we're going to explain the naturality of flat representations, like where do they show up in nature. Then we'll relate them to local Galois cohomology, which will allow us to state and complete most of the proofs of Ramakrishna's main results, but not all of them. Then we'll cover the required results of Fontaine, which will allow us to complete the proof of Ramakrishna's representability of the flat deformation problem that I promised above. This will yield a theorem about Galois cohomology, whose residually split ordinary counterpart we will also prove, even though I don't think we need it. We will need the theory of the neuron model of an elliptic curve throughout. The canonical references for this topic include Silverman 2 and Bosch, neuron models. Okay? So, the notation for the chapter will be as follows. We'll fix algebraic closures Q bar and Q bar L for all places L of Q, as usual, as well as embeddings I sub L of Q bar and Q bar L. For any field K with fixed separable closure K sub S, we'll let G sub K be the Galois group of K, the absolute Galois group. We'll let G sub L and G sub Q be the decomposition group at L, arising from this embedding I sub L, usual stuff. When L is a finite place, we'll let I sub L and G sub L denote the inertia subgroup, again, as usual. All finite extensions of QL will be in Q bar L, and for L a finite place, all finite fields of characteristic L are going to be subfields of the residue field F bar L attached to Q bar L. All right. If sigma is a finite set of places of Q, we'll let Q sub sigma and Q bar be the maximal subextension of Q unramified outside that set sigma. And we'll let G sub sigma be the Galois group of Q sub sigma over Q. When a prime P is fixed, we'll let epsilon from GP to ZP cross denote the p-adic cyclotomic character, and we'll let omega be epsilon mod P. So this will just be the mod P cyclotomic character from GP to F cross P. All right? We will be allowing P equals 2 in this chapter unless we state otherwise. All right? So that's important to keep in mind. So we're going to say finite flat S group scheme without mentioning the assumed commutativity, first of all. And also, there should also be a finite presentation assumption, but we're always going to have an Noetherian base scheme S. So we're not even going to mention the finite presentation assumption because it's going to automatically be fulfilled because of that Noetherian condition. When S is spec L, where L is a field, we will just write finite L group scheme instead of finite spec L group scheme, as usual. The notation X over S refers to a group scheme X over the scheme S. And if S is spec A, we'll just write X over A instead of X over spec A. For certain group schemes G over the integers, or FP, like the multiplicative group scheme, alpha sub P, which is the kernel of the P power map from the additive group scheme GA to itself, where P equals 0 and the final object of whatever category of schemes we're in. I kind of mentioned this definition here because I don't think we actually talked about this back in chapter 5, which was the chapter on finite flat group schemes. Okay, so GM, alpha P, and then mu sub P. So this is the scheme of Pth roots of unity. We're just, for any scheme like this over Z or FP, when we write G over T, what we mean is the base extension of G to a given scheme T.